Welcome everyone to another CP Tap call. This call number 160. Our speaker today is Steve Kolta, which is a broadcast application engineer at Meinberg USA. Steve supports supports the broadcast consultant, integrator, and end user in designing synchronization solutions and network for ST2110 and emerging IPMX standards. He brings 26 years of experience in broadcast industry and is an active member of the AIMS, VSF, and the IPMX Standard Committee. Steve is also part of Meinberg's development team, helping define new broadcast solutions. He holds an electrical engineering degree from the DeVry University in New Jersey. Please join me in welcoming Steve Kolta.
Thank you, Ahmad, and welcome everybody. And thank you for taking some time to go over the slides. And what we're going to talk about this morning or this afternoon is validating broadcast media sync in our operability. So why is time synchronization essential in broadcast media? At one point or another, we all seen the clapboard. And I'm hoping a lot of us know what it was actually used for. Does anybody know? It was actually used as a reference for multi-clocks and multi-cameras. So as you may know, in many environments, there is a need to videotape and compose the pictures in many angles. So a lot of cameras are used for this, and to synchronize them, you need some sort of a reference device. As primitive and as simple as it looks, it really did a good job with the analog signal. And as we move on to the new world of everything going on the internet and going over the cloud, everything goes over, and the need would be the PTP. And why PTP is needed? Well, let's see if we can discover this on the next slides. So like I was saying, on many application, multiple cameras, audio, and metadata are captured on separate equipment. For instance, there are SLR cameras, there's broadcast cameras, there's cameras from drones. There's also multiple sources for audio that needs to be captured during any one event. So you have ambient sounds that needs to be captured during, let's say, a sports session. There's microphone that needs to be captured from commentators. There's microphone that needs to be captured from advertisement agencies. And there's also metadata. Metadata could be in different formats. Some of it, and most importantly, are for closed captioning and color matching and color gradings. So let's take a look at an application, for instance, a stadium, let's say a Super Bowl. What goes on in there and what kind of equipment is needed and why synchronization is needed. This is a very simple, grossly oversimplified diagram of what can be used. But if we look from the left side, we start with multi-cameras, multi-microphones. And I'm sure we'll also, at one point or another, those OV trucks outside with the satellites or open broadcast trucks. And what's inside those trucks? There's actually a lot of equipment, probably in about $1 million worth of equipment. And they really do the magic in getting all of that going. And then from there, they basically take the signal. Once that signal is kind of edited and synchronized, and they send it off to a broadcast station. So let's take a closer look. What's inside these OV trucks? Well, we're going to concentrate basically on the synchronization part only. Obviously, there's a lot involved, but what we are mainly concerned with is what is really going on with the, getting the signal from those audio and those video. And just kind of getting all of that together in sync. As we know in broadcast, there is really no second chance for failure. It's high visibility. Everybody's watching this in real time. You cannot have any failure. And because of that, you need to have a failover. So for that, you need to have a red and blue networks, if you will, for synchronization. And there's routing panels, the control for engineering, there's diagnostics, there's PTP that's going on, there's texting and stream encoders and decoders and multiviewers. Really, there's a lot inside of it. And basically, what they do is they get all of this into one edited stream, and then they send it off to a CDN server over probably dark fiber. From there, that signal gets transpired to a station, broadcast station, and then from there, it gets to us, the viewers. We get to watch it. So, um, in the analog world, everything transpired basically over SDI. So, what is SDI? SDI stands for Serial Digital Interface. It's basically a coax cable like the one you see on the antennas, except it's 75 ohms. It uses uncompressed and basically transfers uncompressed data. It uses analog for payload, blanking, and multi audio channels. And as we know, everything is going over IP now, so we're going digital. And with the digital, everything is going over network switches and fiber optics. So the audio industry was basically the first one that kind of adopted the IP technology. And why is that? Is because it was kind of really more of a easy fruit to pick, and it didn't take that much bandwidth. And if you remember in the older days, the network were really in the hundreds or in the megabytes, and then it went on to 1 gigabytes. So it made sense for the audio to kind of adopt this in the beginning. And one of the earlier adopters were Ravenna Audio, AES67, and other audio over IP standards. And from there, PTP version 2 was kind of composed. Meinberg became one of Ravenna's partners back in 2014, and they were really one of the first that took a step to work with PTP and ratify ST2110. Two new IP standards with the infrastructure started off with PTP version 1, and that kind of moved on to version 2 by 2015. PTP was chosen as the sync method for the beginning. Why is that? Because you needed something that's under 1 millisecond. We're in the microseconds accuracy. And as we all know, NTP was not good enough. So that's why PTP was kind of chosen for that. That was chosen by SMPTE, which is the motion picture engineering group, and they created the profile. And the profile for SMPTE or broadcast was the ST20 2059-2. Many interoperability events took place to ratify this. There were several IP standards that came together to do this. And from there, SMPTE 2110 Suite was born as the standard. So what is ST2110? Basically, it's a standard, again, established by SMPTE committee. And basically, in its simplest form, it states that audio, video, and ancillary data need to be transitioned and transpired over three separate essence over multicast. It uses RTP, real-time transport for transmission. It implements STP or session description protocol. And that's basically a file that kind of tells what kind of data is coming and what's the parameters of the data that's coming and the resolutions and how many audio tracks and what kind of metadata and so on and so forth. And it does require PTP synchronization, as we stated before, with the profile 2059-2, and we'll cover that on the next slides. So the structure, again, the structure was ST2110-10, -20, -30, and -40. The -10 is basically the timing and synchronization as defined by the SMPTE 2059-2 profile. The 20 is the video uncompressed. The dash 30 is basically the PCM or the audio. The dash 40 is the ancillary or the metadata. So those four together define the ST2110 suite. This, again, it kind of started off at 2014, and by 2017, it got ratified and it got tested with SIMT, AIMS Committee, and VSF. So let's take a look at SDI, which is the analog world, versus the digital world or the IP. What are some of the advantages of SDI? Well, first, its familiarity. It's been around since the late 80s, early 90s, and it was embraced by a lot of the expertise, a lot of broadcast stations. The cost was incremental. You kind of add on as you need, and you expand it as you go. Security obviously has always been, something that everybody worries about, and so it's fully secured. Why that is? It's because it's on a wire, right? You cannot really hack it. You cannot really infiltrate it. You cannot basically splice it. It's low risk. The connector on the BNC, it's basically a lock connector. You could lock it and twist it. And so really the failure is low risk on it. What are some of the disadvantages? It's inflexible. It's a coax cable. It's to run a lot of these cables take up a lot of space and you could trip over it. There's obviously distance limitation. On a 4K signal, for instance, you're limited to like 40 or 50 meters. It's susceptible to noise and electromagnetic. There's a lot of cable, again, it's just very heavy and very complex. The footprint could take a lot of space and it cannot transport over public or the internet, obviously. You cannot go from one location to another. You kind of limit it to the distance. What about IP? What are some of the advantages? Well, we know it's easy to transport using off-the-shelf network switches. You could enable remote productions. You could go from one building to another. You could go from one state to another. You could go from one country to another, basically. The cost, you could leverage it per scale. It's much smaller footprint. For instance, you could take a switch, a Netgear or an Arista or Cisco switch with 48 ports, and it only takes one RU high. It's faster pace of innovation. A lot of the IT world obviously could grasp that, and they could understand it much better than talking, broadcast technology. And of course, we know that fiber is immune to electromagnetic. Nowadays, all the new buildings, basically, when they construct a new building, they just build it with dark fiber. So the wire is there and it's easily accessible. What are some of the disadvantages? Well, it's expensive for one. We know that fiber, although it's gotten much cheaper than what it used to be, it's still kind of expensive to rip off an infrastructure that's been around for 15 years, the SDI, and kind of rip it out and start all over again. The learning curve in the education. A lot of these broadcasters been there for a long, long time, and they're like, they know that SDI works, and they're kind of hesitant to kind of replace it with networking. And needless to say, it also requires knowledge and getting up to speed and knowing all there is to know about network and security. Multicast routing. It's not like everything could go on the network because eventually, obviously, you could flood your network if you don't properly put the guards necessary for it. Security is always a concern, of course. So why is time synchronization essential in the IP? Well, we kind of touched based on that. Because we're transporting the audio, the video, and the metadata separately. And of course, it's like, three cars going on the highway at three different speeds, and they need to be clocked and they need to be synchronized together. And most of the time, because it's going to be a hybrid application, they're not going to rip out those broadcasters, and those stations are not going to rip out their infrastructure and just start, at the flip of a switch and say everything is going to be IB. Everything is going to be IP. It has to be kind of like, a slow transition. So a lot of these designs are both analog and digital together. And so there has to be equipment that's going to take care of this. Each of the multicast streams get an RTP timing. So there's hardware stamping that goes on with the packets. It goes out with the transmitters and it gets received by the receivers. There's also iframes. Iframes basically kind of tells or dictates what kind of video frames and the packet size. And there's also the time code labels. So all of this is stuff that kind of happening on the network. Let's examine PTP in an IP-based studio, for instance. In its simplest form, we're just going to talk about audio and video, and we don't need to talk about the metadata for now. So if you look on the left side, we have an audio transmitter, and we have a video transmitter, and we have a PTP clock, and then our network is in the center. And on the right side, we have receivers. So to begin with, the P2P Grandmaster is going to distribute PTP for both the left side, which is the transmitters, as well as the right side of the network, which is the receivers. From there, the transmitters and the transmitters for the audio and the video will take the data or take the analog signal and the video signal, which is turned off as analog, digitize this and put it on packets as packets on the network. And as you notice, when the packets are leaving those transmitters, they are in sequence. So there are sequence 1, 2, 3. And as they go into the network, they're still in sequence. However, when they come out of the network, they're no longer in sequence. So on the right side, you could see that they're, 2, 4, 1, and 3 no longer in sync. And that is because the network switches are trying to optimize transportation. And in the midst of trying to optimize the data, it actually throws it out of sync. And because of that, they're not going to be in time anymore. So it's the receiver job to kind of take care of this. It looks at the timestamps that came from the transmitter and it compares them to what it has received and it puts it back in order. Excuse me. So the transmitter takes those and puts them back in sequence. And after that, it does the job of possibly taking the ST2110 and transferring it back to, let's say, SDI or HDMI or just native 2110. But the end result is that stream is going to be in sync. So like we were saying, broadcasters, they're typically been doing that for a very long time, and they're kind of used to doing SDI, and they're happy with it. So it kind of takes time for new technology to kind of, take over and become the standard. So if we look at, for instance, data centers and telecom, they embraced PTP and timing synchronization since the early 2000s, where broadcast is kind of more of the latecomers. They're coming into this in 2014. And it wasn't ratified, like I was saying before, until 2017. So it kind of takes time for this whole, transfer of data and information to kind of become the standard. So why is it taking too long? Well, as we talked about earlier, the infrastructure for SDI has been there, and it costs a lot of money, and it still works. It's resilient. It doesn't really fail. So, why, like they say, if it's working fine, why should you, change things? And IP2110 still, even though it's been around since 2015, it's still the new kid on the block. The expertise, like I'm saying, people that have been doing this for 20 years, they need to get educated on 2110 and become familiar with all the IT stuff and the network, into transportation and the security and so on. And as we know, as we go, everything gets refined and gets updated with the firmware. So there's constantly bugs that need to be discovered and it needs to get fixed. And there's constantly features that being deployed. Um, so what can Meinberg on the side of timing could do to help this? Well, we decided to kind of take this and do some certification and ratification and testing for interoperability with regard to timing and synchronizations. There are different vendors that supply networks, switches, or vendors that supply gateways, um, encoders and decoders. And even though it is open standard, we talk about open standards, but do they really work with each other? When you take three, four, five different brands and mix them all together in a bag, do they all work the way it should be? Um, so to begin with, we need to address what are the timing requirements and what are the specs. Like we were saying, SMPTE committee provided the specification for 2059 back in 2021. And so there are grandmasters, there's followers, there's default profiles that need to get followed, there's frequencies that needs to get followed. There's also the JTNM committee, which is Joint Task Force Network Medium. This is basically a nonprofit, and they took the SMPTE profile and they ratified it and they tested it, and they even refined the specification to another level. So if you talk in multi-channel audio, for instance, which we know, surround system, for instance, 5.1 or 7.1, that's a multi-channel. They said that the synchronization needs to be within those different channels of audio down to 10 microseconds of being efficient. The followers, for instance, you need to be like any follower or any encoder decoder need to be able to lock into the signal within five seconds, and it needs to be an accuracy of 1 microsecond. Multi cameras, like for instance in a game and whatnot, you could have something in the numbers of 10, 15, 20 cameras together, and those need to be in sync with each other to within 2 microseconds. Uh, so why does time need sync? Well, we talked about because there's different multicast for the video and the audio and the metadata. And without them, you're not going to have smooth transition in the video. When you're switching from one video camera to another, it needs to be smooth. It solves the black frame without the synchronization because there's no reference. You're going to end up with a black frame in between because you're kind of dropping data or the data is not getting there in time. And as we know, that kind of really comes down to phase and frequency together. It prevents jitter and artifacts, color matching and synchronization or color grading. Within different cameras, even though they're in the same environment, each camera has its own parameters, and you kind of need to match that color. Otherwise, when you switch in from one camera angle to another camera angle, you'll see that the color is not the same. Also, audio and the video, they need to be in sync together. I'm sure at one point or another we saw some of those international movies where, the lip sync, the audio and the video just don't match together. And there's a lot of reasons for that. One of them is because audio takes a lot less bandwidth than video, so it's going to get there first. So obviously we need to delay the audio so the video can catch up to it. You could also hear pops and crackling in the sounds if you don't properly time it. If you switch them from one source to another, one source could be, 3 dB in audio level lower than the other one or higher than the level one. So those need to be balanced together during the switching, and timing has to do a lot with this. It provides audio, or prevents rather the audio drifting because, like we were saying before, the audio is going to get there faster than the video, so it need to be timed or held back together. Ancillary data, closed captioning, obviously, as you're translating, from one language to another, and you're seeing, the lips are moving, you need to see that data coming at the same time or at the same rate as the video. SDP session is basically your session description protocol. Basically, it's a file that get transferred or transported along with the audio and the video. And it basically tells what kind of data is coming in those files, what kind of resolutions for the video. Is it HDR? Is it standard def? How many channels of audio? Is it two channels of audio? Is it multi-channels of audio? And so on and so forth. So what are some of the interoperability challenges? Well, there are different kind of PTP modes, as we know. There's boundary clock, there's transparent clock, there's end-to-end, there's leaders and followers, there's multicast modes, there's redundancy or 22-7 in the SMPTE world. And what are some of the challenges? How long does it take for a device to lock to a PTP? We talked about having two versions of PTP. When PTP first got introduced, it was version 1, then it's version 2, and there's 2.1. So the system needs to be aware of all of these things and what version is running and are they compatible with each other. And what happened during source switching? Does the receiver drop video? Does it drop audio? And what are, the symptoms that happens when PTP is lost? It is quite different from one device to another when you compare them. So it's important to kind of know all of these things in advance, especially for somebody who's trying to architect a new design for, let's say, a TV stations or a studio. It's kind of knowing the unknowns, so to know what to expect and how to adjust for that and how to fix it. What about redundancy and failover? As we know, broadcast is live. There's really no second takes, and if something fails, it doesn't look good. So there need to be a failover mechanism. So the P2P kind of need to be on both the red and the blue networks, and we'll take a look at that next. So we were saying standards are vital, but they actually need to be proven and need to be followed. Otherwise, they're just not going to work. It's kind of nice to have a standard, but if we don't improve it, it doesn't really mean much. So how does interop validation could diagnose and eliminate that? Well, we want to start with a reference test environment. We want to have a reference video, a reference audio. We need to have a reference networks, displays, and of course a grandmaster to test all of that stuff. We need to have SDI, a mix of SDI analog signals and HDMIs. We need to have audio, and we need to have network switches with SFPs and fibers to test all of that stuff. We need to establish a list of tests. So obviously we need to identify, what needs to be tested and how are they going to be tested and what are the parameters to be tested as well. And of course, we need to have monitoring and diagnostic tools to confirm all of that output. And of course, we need to invite device vendors, edge devices, encoders, decoders, switches. We need to invite different vendors to give us their products and test it. And we're not doing this to say, well, one brand is better than another brand. We're just doing it so we could establish a standard. And if something is out of the parameters or out of the standards, we would tell that vendor, hey, Mr. Vendor, we noticed that these things are out of spec. What can you do and fix it? So This was kind of done with of course, it needs to be a non-biased entity that kind of do that. And the European Broadcast Union kind of took on this task and they did it. And they did a lot of testing, hands-on testing, and those testings were shared, and they continue to be ongoing. And of course, those tests need to be documented and provided to the people or to the vendors that participate in that. But from Meinberg side, what can we do to test these devices on the grandmasters, our grandmasters? Well, Meinberg developed MISTI. MISTI stands for Meinberg Studio Test Environment. Basically, it's an interoperability test rack or test environment that we kind of took it upon us to test different vendors and different gateways. And what is inside the MISTI rack? Well, there's a mix of SDI sources, there's playbacks, there's distribution amplifiers, there's encoders, decoders, there's switches, there's grandmasters, there's dual monitors, there's speakers. We're testing the whole thing from A to Z with regard to timing. So to break it down a little bit, there is input reference sources. So we use an SDI player from Blackmagic. We use content rather than showing graphs and timing, deviation and whatnot. Those are always nice to see, but in the broadcast, they're more of a visual people and they like to see things as a result. So I'm a big Rush fan, and I decided to use Neil Peart because I think he's a good drummer. So I'm using his videos to see how we could synchronize the audio and the video together. We use in distribution amplifiers. We use in redundancy red and blue networks, obviously. And we use a network one to transfer the media, which is really the red and the blue air gapped. And we're also using out of band control switches, two grandmasters for redundancies, decoders, and on the output side, we use in monitors to look at preview the audio and the video. And then we use in decoders to decode that ST21 signal back to HDMI or SDI so we could view that on a monitor. And also we're monitoring the speakers. From a diagnostic point of view, we're looking at a control management switch. We use in PTP TrackHound. Some of you may be familiar with it. It basically monitors the PTP traffic for monitoring and diagnostics. We're using SyncMon to diagnose the signal. We use in preview monitors and HDMI displays, speakers, and stopwatches. And what devices are being tested? Like we said before, encoders, decoders, switches, and PTP grandmasters. This is really more of a high-level design of what goes inside of it. On the left side, we have encoders or source. We have a source, and then we have the encoders, and then we have the red and blue network switches. We have the P2P grandmasters over here, and we have decoders on the right side. And up on the top, we have the monitoring system, we have the audio, and we have the video displays. So what are some of the results that we tested? In some details, we found that some of the vendors were dropping audio packets. Some vendors were dropping frame sync or video. The frame packets, if you will, there's a limit for how much they can be. Some of them turn out to be less. Some of them turn out to be more, and because of that, they're out of spec, and therefore you could drop a frame or two and that ends up being a black video. There's two different kind of audio level, if you will. There's level A and there's a level B. And if both of them are not supported, again, you're going to see disturbance in the video signal. One vendor was dropping audio completely when PTP goes away. I mean, some of them drop it and it comes back. Some of it drop it and it never comes back. One device dropped the audio for 23 seconds and then it came back. Another drifted pretty much for about 5 or 7 seconds. That's a lot of drifting in the audio. One vendor dropped video and audio, even though you're supposed to have a redundancy. So the redundancy basically, if one stream is lost altogether, you should not see as a viewer any disturbance because the redundancy kind of there's two streams that go on in parallel at the same time. One vendor was claiming to be a boundary clock, even though there should be just followers. Otherwise, they could just hijack the network from a PTP perspective. And then some of them, the delay request, as we know, per the profile from SMPTE, they kind of need to adhere to the standard of the profile, and some of them were not in spec. So in summary, most of the devices work well, but don't really, match every standard that's specified, and some of them kind of needed to be adjusted. Some of them failed the redundancy altogether. So what are next steps? Meinberg continued to do some of these testing and continue to do collaboration with different vendors. And eventually we would have a list of all the vendors that we tested. And again, it's not saying, brand A is better than brand B. It's basically saying these are the models that we tested with our grandmaster and we know how they behave. This gives the architect or the designer a peace of mind when they're putting a system together, and also gives the vendors a chance to kind of correct or fix some of the parameters that they need to be the same. And then the same for IPMX. Well, what is IPMX? IPMX is the next evolution in Pro AV. So in AV, there's really two different markets and two different verticals, if you will, and they're kind of merging in together. There's the broadcast that most of us know, and there's also the Pro AV market, which is more of a commercial. And the Pro AV, not necessarily in real time, but it still requires in-time delivery of the audio and video. So Internet Media Experience is what it stands for. It's basically following the standard of ST2110 because it's been around now for a while. And if it's good enough for the broadcasters to embrace, well, it's good enough for Pro AV as well. It was developed by Ames. And again, basically covers most of the standards that ST2110 covers. So far, there's 36 companies that's embraced this, and the list keeps growing. And what are some of the differences between the ST2110 and IPMX? Well, because it's Pro AV, they don't have the luxury of having a non-compressed network. So rather than going on a 25 gig and 100 gig switches, we're operating or they're operating into 1 gig, maybe 10 gig. The focus is on mainly two-channel audio versus multi-channel. There's HTCP and EDIT, which are mandatory by HDMI. And again, we said that it goes on 1G and 10G network. It is compressed versus the 2110, which is non-compressed. And it adds codecs such as JPEG 2000, JPEG XS, which lightly compress the signal so it can fit into the 1 gig or the 10 gig network. And one big differentiator between the two is PTP is optional. Why that is because, again, you're dealing with less audio channels and it doesn't need to be in perfect real time. So sometimes you could use it in a synchronous or asynchronous mode, which puts PTP as an option. Some of the IPMX events that happened started off in March. There was one at the NFL in Los Angeles. Another one took place in January 24. Another one took place in Everett last year. And then as of late, we did one in January in EBU in Geneva. And there's another one to follow in August in the next couple of months. And that's basically what I have and the time slotted. I hope I wasn't going too fast. And I invite you to, if you have any questions, I'd be more than happy to answer them.
Thank you very much, Steve. Yeah, let's open the floor for questions. Sorry, that's like my toddler screen here. So maybe I can put a like an icebreaker. How are, let's say, for example, the advancements in network and switches? Sorry about that. So the advancement in network and switches that, like, caused mainly by AI, improving, let's say, the gears that you use, because I mean you use also packet switches and so on, like, the hardware that you have in your field.
So I mean, yeah, that's that's a great question. With AI, it's kind of taken over and a lot of the things that we do. And I really look at AI, at least in the broadcast spectrum, as a muscle for say, it kind of could do a lot of things much faster and much more efficient than we humans could do, but it's not really kind of taken over. I mean, some of those advantages really goes with the diagnostic and looking at the packets. Like I was saying before, it started off with 10G. Now we're kind of like in the 50G roams and 100G. So, the computations for the error FAC and uh, the optimization of the speed of the networks are obviously probably getting better with AI. But as we all know, this is just new. So discovering, maybe artifacts or stuff that could be out of spec by having diagnostics can be probably improved upon with the AI. But yeah, I mean, we're getting, network switches now for a lot less expensive than they used to be. We're talking maybe, in about $10 or less per port, where it used to be like $100 per port in the older days.
So, I mean, a follow-up of that is, like, I'm just curious to know, like, for example, with the demands that we have for AI, we have like, the improvements and, like increase in capacity and whatever, all of these things. As you mentioned, like, we went from like, I don't know, 10 gig, 25, 40, just go all the way up 100. So is that also making differences, like how you have to treat, let's say, for example, the SIMT 2110 protocol or things like this? Like, do you need like something then, like, I mean, going toward IPv6, IPv8 right now is like on the horizon, things like
Yeah.
that?
I mean, yeah, I mean, very well. I mean, we're still operating under IPv4. 6 is already supported. But as we move along with these, I would say yes. Hasn't been really much of testing because there has not been really much of a demand to go over the IP address limitations of IPv4, if you will. But a lot of the manufacturers, as we know, already support IPv6. Haven't seen the V8 yet.
Great. Anyone else?
Yeah,
Hasham,
I have a question.
go for it.
So, this is very good presentation actually. Uh, are there any security issues that still outstanding and need to be resolved for this whole thing to work?
Uh,
Security?
Definitely. So this is something that I really haven't touched on a lot with the presentation that I have, but there are definitely a lot of security protocol, if you will, and that's going to change from one application to another, of course, and from one vendor to another. But SIMT and there's also the control part of it, which is NMOS. So NMOS is the control mechanism that I really didn't cover at all. But as we talk about standard, obviously there need to be a standard for the way we transfer in the audio and the video, as well as controlling the data. So from a control perspective, if you have different vendors, they all need to be controlled by one, one protocol, one API, one REST API or JSON commands. And within that NMOS infrastructure is the security protocol. So there is IS, for instance, IS 11, which cover the security protocols of the NMOS part of it, and there are different set of standards for it. And obviously that also need to be tested. So it varies from one to another. A lot of the guards that was kind of put with that is having the platform on a Linux rather than, something like Windows or whatnot, because we know that Linux is more of a more secure, not secure, but open environment that can be controlled better or less immune to viruses. So to answer your question, the long question and the long answer is yes, there are certain standards, and that's part of the NMOS protocol.
And yeah, and I noticed, as you said, you didn't cover in mass. Uh, so maybe you should have another presentation just to focus on security and in mass. What do you think?
I think it's great. Yeah, it's a great idea.
And I think
Yeah,
Hisham, maybe you can arrange it in your thing because
yes,
yeah,
we can do that, Ahmed.
yeah, yeah.
The reason I talk about security because Doug keep on saying that the security is one of the biggest challenges for time synchronization, at least from Meinberg perspective. But
Yeah, it
thank you
is.
very much.
Yeah.
Thank
Mm. So one more thing, like just wanted to add, Steve, like when it comes to OCP. So like basically what I heard, like and then I mean, congratulations to your work. Interoperability and making sure things work like in an ecosystem is one of the things that OCP promotes and OCP tries to do the best. So I think perhaps we can have longer conversation and discussions to see how this whole thing, like can be brought up, let's say, under OCP's umbrella, because it is its own kind of a network, but yet similar hardware, and I see it getting converged. Like the reason why I was asking, like, what's going on? Let's say when AI pushes, like all these switches to get better and so on, is that affecting, let's say, your world? And it looks like the answer is yes. What let's say with slower pace, but still, it's the same hardware. It's converging. It's not like uh, divergence. So perhaps we can dig in those things. Anyways, anyone else? Any more questions? If not, I can give you 10 minutes back. And again, thank you again, Steve, for today's informative presentation. And like we learned a lot about like what in broadcasting, like the relevance of timing and everything and network and all of this in broadcasting world. And we'll see everyone in 2 weeks for a talk by our very own Greg Armstrong. But EPPS, that was like EPP Cylon, precision at the edge. Great. We'll see everyone in 2 weeks.
Great.
All
Thank
right.
you.
Thank you. Bye, everyone.
Bye.
And